Good day, students. This is week 4. Okay, we are entering week 4. So this video serves as a recap for week 4's content, as well as the tutorial. Okay, we've all primarily looking at the expectations and variance. Okay, expectations and variance. So for the expected value, it is the long run average of the value of the random variable. So it's a long run average. So here, if you throw a fair dice continuously, then for each of the value on the face, 1 or 2 or 3 or 4 or 5, each of them will have the probability of 1/6. So expected value is the average number of all the observable face value on the dice. So the formula here is EX equals to the sum of all the possible values, like so 1, 2, 3, 4, 5, 6, and its corresponding probability. So for a fair dice, the probability is 1/6. So 1 times 1/6 plus 2 times 1/3, 6, and so on. So it'll be basically 1 plus 2 plus 3 plus 4 plus 5 plus 6. Sum them together, divided by 6. So the value is 3.5. Okay. So then there'll be a few other examples. So for example 2, when we're looking at the probability is different for the different $5, $10, $50, then you can calculate according. So refer to the video, then yeah, expectation. So this is expectation. Then for 4.2, expectation properties. So first property is the linearity. So if you have a coefficient times the random variable, then the expectation of alpha x1 is equal to alpha times expected value of x. So there's linearity. So property 2 is if x and xy and x2 are statistically independent, so they are independent events, then x1 times x2 is equivalent to the expected value of x1 times x2. So these are the two properties that we'll use. Okay, two properties that we'll use. Okay, cool. So the 4.2. Then for 4.3, we'll move on to the variance. So the spread of a distribution. So the spread of the distribution can be measured by variance. So this is a universal variance formula. So yeah, mu is the population mean, so or the expected value of this random variable. So this is the standard formula. So here is the example, right? So x is -1, 2, 3, 6. So there is 4 values. So the frequency or the probability is provided to you here. Then x times fx is x times fx. X times x2 times fx2, x3 times fx3. So you have these 4 values, which is these 4. So the EX expected value is the sum of all these 4 numbers. You get 2.8, right? So that's a mu value. So x minus mu is -1 minus 2.8. You get -3.8. Then 2 minus mu, 3 minus mu, 6 minus mu. So you get x minus mu, right? Then for each individual, you square. Then you get a squared x minus mu, right? These 4 number. Then you use these 4 number times its corresponding probability fx. So 14.44 times minus 0.28 or 225. You get this list of 4 numbers. Then variance is just the sum of this last row. Okay, so that's the standard formula of calculating variance. So in the meantime, we're at week 4. So everything we are touching now is primarily population. So this is a variance to calculate the population variance. So move on. Okay, the square root of variance is standard deviation. So population standard deviation is sigma. Okay. So we also look at this. This is the for normal distribution with mean value expected x value equals to 0. All of them are centered at 0. Okay, right, 0. So, but each of them have different variance. Variance 1, variance 2, variance 4, and variance 8. You'll notice when the variance goes larger and larger, or the standard deviation goes larger and larger, you'll see that this curve gets flatter and flatter, move towards the two tails or two sides, two tails. Okay, so when you want to ensure the area under the curve of these four functions, the total area on the curve must be 1, So when you have more area at the two sides, two tails, there's more area near -4, +4, there are more area there. Inevitably, you need to compensate by reducing the area in the center. So earlier, in the standard norm, zero mean univariance, you see a higher peak here, a high peak here. So when you spread to the two tails, inevitably, in order to maintain the area under the curve to be equal to 1, you need to reduce the peak of this curve. Okay, so this is the probability density function. So you need to reduce that one. So to maintain the area under the curve equal to 1. So that's one of the most important concepts and observation that you need to remember. There are a few properties of variance. Variance calculation is nonlinear. So if you have a coefficient times the x, then that coefficient, if you want to move it out, then the coefficient need to have square. Okay. Then if you have a constant inside, let's say you roll a dice, the dice shows a face value 1 to 6. Okay, shows a value 1 to 6. Right. Then if you add these numbers, each of the number I add 10. Okay, now it become 11, 12, 13, 14, 15, 16. Okay, then you add a constant of 10. Then the variance won't change. If you still recall, the variance for the fair dice is about 2.9, around 2.9. So if you have a fair dice showing 11, 12 till 16, the standard deviation doesn't change. I'm sorry, the standard deviation and the variance doesn't change. And the variance, will still be around 2.9. However, the expected value changes. So earlier it's 3.5 for 1 to 6, right? Then if you are now moving from 10, 11 to 16, you have add a constant c equals to 10. So expected value will be 10 plus 3.5, so 13.5, while the variance stay unchanged. So if you are using a fair die, say 1 to 6, then I have an alpha equal to 2 now. So you multiply 2. So 1 to 6 now becomes 2 1 to 6. Let's have a look. So let's say so 1 to 6. This is 1 to 6. So I use 2 times 1 to 6. Then you have this value, right? This is a value. And now, your expected value and the things will change. Let's see, x equal to this, c 1 to 6. Let's calculate it. X 1 to 6. X is this, and let's display x. Then we have expected value of x equals to x times fx. So x times fx is 1 over 6, right? So we are just timing. So now okay, x times 1 over 6. You have this number. Then you sum them together is the expected value. Okay, you sum them together. Then this is your expected value. EX, right? This is your EX, 3.5, not wrong, right? So we can also calculate variance. How do we calculate variance? So this is the mean value, right? Just mean value. So this is 3.6, 3.5. Then x minus 3.5. This is the x minus 3.5. Then we square it, right? So square it. So this is the square. Then you sum them together, then you get the variance. So this is the variance. Okay, as times the probability. Times the probability, which is 1/6. Okay, sum them together. So 3.9, around 3.9. So this is the variance of x, right? So now we say y equals to 2x, right? 2x. Let's say 2x, right? Y equal to 2x. So now I have a y here. Y is now to so now we are looking at if y equal to 2x, then what is the expected value of y? Okay, so y is now this, right? So, the probability is still the same. So instead of x, you change to y. Then you check y. What is the value of y? What it is expected value is 7. So it is 3.5 times 2, right? So it is 7. Okay, then what about the variance of y? Variance of y, we again use this formula, where variance of y. So instead of x, we change to y, sum y, everything is y. So it is y. So y becomes 11.66667. Then we want to find out whether this is correct. So according to the formula, if you are y equal to 2x, then the variance should be 2 powered 2 times the original variance of x, right? So the original variance of x about 2.9, and time it together, you'll still get the same 11.6667. So that means, yeah, so if you manually calculate variance y, it's 11.6667. Okay, now we change this one, say instead of y equals to 2.2 times 6. I'll say earlier, remember, right? We say plus 10. So now y is it that dice give you 11, 12, 13, 14, 16. Then again, we'll have a look at the expected value of y. So now it's 3.5 plus 10, right? So 3.5 plus 10, they give you 13.5. Then the y is the variance of y. Variance of y should not be changed, right? So since it's adding a constant, to it. So it's adding a constant c, right? So if you add a constant c, there is no impact on variance, but there is impact on expected value. So variance remains same, 2.91. Okay, so that's the one. Okay, so we have demonstrated this property of variance. This is pretty important. Then, okay, then let me close this one. I can close this one. I can also close this one. Okay. So now let's move on to here. Okay. Now let's move on to the tutorial. Okay, tutorial. Tutorial. So let x be the Bernoulli random variable from the Bernoulli distribution with success probability of 3. That is, assume that x is either 0 or 1 with probably 1 equal to 3. Okay, x equal to 1 is 3. What is expected value of x? What is variance of x? So we just use the formula. We use the formula. Okay, let's open this tutorial solution. Okay, expectation question 1. Find the expected value. P equal to 0.3. Let me clear this variable place. Okay, let's clear it. So probability 0.3. Okay, expected value of x. Expected value of x equals to P. Okay, so this is quite straightforward. So, okay, this is the formula. This is the formula here. Okay, so expected value equals to all the x. Right, so all the x. So X can take 0 or 1, right? X can take 0 or 1. Let's do this. X can take either see 0, 1. So this is X. So let's have a look at X. X can be 0, 1. Okay. So when the probability, the E probability, X equals to the sum, then X times the fx or the probability. So that's the one. Let's sum them together. So now X, okay, let's do this. X1 equals to 0. X2, this is the one to find out what is the value of X. Okay, X1 times the probability is 0.7, right? So then plus X2 equals to 1 times 0.3, which is a probability. Basically, this is a probability. Yeah, so you got 0.3. Okay, right. So 0.3. So your expected value is equal to the p-value, the probability of X equal to 1. So it is 0.3. So next we look at the variance. Variance, again, we use this formula. So we just use this formula. X minus expected X. Expected X is 0.3, right? 0.3. Then square it, sum them together. Then this will give you X minus 0.3. So you 1 minus 0.3 squared with 0.49. 0.49 when X equal to 1, they give the probability of 0.3 if time it. Then when X equal to 0, then 0 minus the mu value 0.3 squared, which is 0.09. Then time the probability when X equal to 0, so 0.7. Okay, so the variance is 0.49 times 0.3 when X equal to 1 plus the X equal to 1. So 0.09 times 0.7. So you get 0.21. So that's the variance of question 1B. So the variance 0.21 is actually the P times 1 minus P. So that's another way to calculate the Bernoulli variance. But I recommend you just stick to the standard formula because R is actually quite good at calculating numbers. Okay, so this is B. Question 2. Question to find the expected value and variance of the random variable. So A is X is outcome of when we roll a fair dice. Y is an integer between 1 and the 0 chosen at random, inclusive. Then C is X times Y, and X and Y are independent. Basically, you find the expected value and the variance for this ABC. So that's for ABC. So that's a question here. So this is a pretty complicated one. So let's break it down. Question A. So we have this X. Okay, let me clear the environment. Okay, so let's start X 1, 2, 3. Also, you observe X is integer 1, 2, 3. Frequency is REP 1 over 6, 6 times. So basically here is REP X equal to this, then 6 times. Okay, so repeat 6 times. So fx, you have 6 members, each of them is about 0.167, which is 1 over 6. Then x times fx is being shown here. So 1 times fx, 2 times fx, 3 times the probability. Then sum them together, you get the expected value, which is 3.5. So we're quite familiar with 3.5 now. So calculate variance. Next is X minus expected X, right? So this X minus 3.5, you get another 6 numbers. So it's still a vector. Then square each of the number in the above squared, negative number become positive or become positive. Then times the frequency. The frequency is 1 over 6. So some learners said instead of fx, just times 1.6, it will give you the same number instead of list. So you can times 1.6 or 1 over 6 as well. So expected x 3.5, then variance is you sum them together. So instead of using fx, you can also use 1 over 6. 1 over 6. So this is the variance, population variance. Let's display it. The population variance tells you it's 2.9167, right? So 2.9167. So if you want to round it, you can do this in the quiz. Sometimes ask you to round. So I say x equal to this value, x equal to this VRX. Then digits, how many digits do you want? I say I want 4 digits. Then it display 4 digits. Now these are the 4 digits to give to you. So there's a tips here. So in the meantime, we're all calculating population variance. There is an R function called VARX. So VARX is calculating the sample variance. It's not a population variance. So it will give you 3.5. It is a sample variance, not population variance. Yeah, because for the R function, it assumes it is sample. So when you have the sample, it use n minus 1, the total number of elements in the sample, which 6 dice, n equal to 6, 6 minus 1 become 5. So in fact, it is giving you a sample variance, sample variance, not population variance. So we will touch more sample variance later. So in the meantime, use the standard formula to calculate the variance. And this is the variance of the population. So for the second one, for a random number integer y between 1 and 50. So y is a integer between 1 to 50 chosen at random, 1 and 50 inclusive. Y equal to 1. You can write this y is 1 to 50, or you can just say sometimes I use equal to assign the right-hand side to the left-hand side. So I just C 1 to 50, right? You can do this as well. So the frequency of y, or the probability of y is 1 over 50. Yeah, simple sample space, equal probability. Now repeat it for 50 times, then you have this Fy. Look at Fy. Fy is just 0.02. 50 times. Then you add them together, it should be equal to 1. That's how I verify it. Sum Fy, you should equal to have 1, that's 100%. So expected value of y, so each of the individual y values, so let's have a look at each individual of y value and each individual of fx value. So yeah, so 1 to 50. Then you time them together, then sum it, right? Time them together, then sum. Then you get expected value 25.5. We can also have a look at this interim step. Yeah, so yeah, that's the one. Then expected y equal to 25.5. Now next we're going to calculate variance. Variance, right? We use these first, y minus ey. So the thing here we're using are quite straightforward, and you can actually observe the values quite easily. Y minus expected y, yeah, minus 25.5. Then next is going to square it. So for me, I can select all of them. Let's say you want to add a square to the entire phrase. You select all of them. Then you press Shift 9. So bracket, give it parentheses around it. Then power 2. Power 2, then that's the power 2 the value, right? So these are still 50 numbers. Then you sum them in time, you can time Fy or you time 0.2 as well. Because each of them has an equal probability, you can just time 0.2. Then you sum them together, sum of these 50 numbers together, you get this variance of y, 2082.5. So let's just use this one to calculate one more round. Variance y, yeah. So we are seeing that expected value and the variance of this y, random number from 1 to 50. So if you use variance, since you have this y, right? So this is a y value. Okay, so these are the y value. Then what if we are using just a internal R function called variance y. You run it, it gave you 212.5, which is not 208.25. The reason here is because the VAR function in R is a called sample variance formula. So this formula is slightly different from the population variance formula. So we'll touch it in a few weeks later. Okay, so at the meantime, just for your awareness, the internal R function variance y, or even or as standard deviation of y, which will give you sample standard deviation, is sample standard. It is not a population variance or population standard deviation. So your population variance is this, then your population standard deviation is SQRT square root of VRY. So this is a population standard deviation, sigma. Okay, so this is sigma 14.43. Then let's say you are using a variance y, fine, that's the sample variance. Then the standard deviation of the sample is 14.57, it's slightly larger than your population one. Okay, you can also do this to check whether the variance is the standard deviation is the square root of variance y. You also get 14.57. So these two are equal. Or ask whether it is equal. Double equal sign will tell you, yeah, these two sides are equal. That's true. It is true. Logically, it's true. Then we're moving to the third one, x times y. Know that x and y are independent. So this is a little bit tricky. So let's do it step by step. Y equals to x times y. So we're going to create a new variable called y, z equals to x times y. So calculate, basically is equivalent to calculate expected value of z and the variance of z. Z is ex times y, and the variance z is variance x times y. Okay, so they are independent. So what I'm going to show you is a way called expand grid function. So this function is good for you to understand its behavior. But I don't think it will be tested in the quiz. Okay, so it's good for you to understand the behavior. So we are creating a data set called XY. It is called expand grid x equal to x, y equal to y. Okay, you can have a look at this function. Oh yeah, that's function shown here. So expand grid, create a data frame from all combinations of factor variable. So you can read through it. So what it's doing. So basically it is doing a Cartesian product. Okay, so x is 1 to 6, y is 1 to 50. So now you have this x, y already here. So you see it's xy, right? Xy, it says 300 observations with 2 variables. Just you click it. You're going to see that x repeats from 1 to 6, 1 to 6, 1 to 6, 1 to 6, 1 to 6. And for y is 1, 2, 3, 4, 1, 2, 3, 4, till 50, till 50. You go to the very end, 1, 2, 3, 4, 5, 6, and 50, 50, 50, 50. So basically it's total possible combinations of x times y. Where x has 6 values and y has 50 values. So in the end, the total number of pairs will be 6 times 50. So 300 pairs. 300 pairs. So imagine that now, yeah, you have a box that you write 2 numbers on it. X equal to 4, y equal to 49. You write that one on a small piece of paper, then you do this 300 times. So you have 300 pieces of paper in the box, then you are going to draw later, okay? So next is manual construction. Also, this is a for loop ways to construct the same thing. This is for you to get to be aware of it. So you can just run the same thing. So I'm going to create some interim variables. Then I do a for loop against x and for loop against y. So basically from 1 to 6, each of the number, then for y, I repeat 50 times. So it is going to create a vector as well. using data frame. So it gives you exact the same result. So there's multiple ways to achieve the same thing, multiple ways to achieve the same thing. And this time you see that actually reverse. So X we use 1 for X for 50 times, and Y is increased from 1 to 50. 1 to 50, then you increase X one digit, so become 2, then Y from 1 to 50, that you do in this manner. So it's different. You can actually sort it and say, I'm going to sort Y. If I'm going to sort Y, say Y is 1. Yeah, you can actually sort it based on which field you want to use first. You sort it, but the total number of outcome is still 300. Okay, next is we are going to create a product. So this product is actually Z. Okay, so we can do this. So I say I can Z. So I'm going to okay, for data frame X and Y, if you type a dollar, you're able to access either X variable or Y variable. Okay, so we can have a look. So these are the 300 X variable. And if you change it to Y, then it gives you 300 Y variables. I'll repeat it. Okay. So what I'm now want to do is I'm going to create a new Z variable. So if you are giving a column name after the dollar and it cannot be found in XY, then I will treat it. You want to create a new column. Okay. And the new columns is equal to the value of X times Y. So just have a look at X times Y. X times Y is 1, 2, 3, 4, blah, 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 blah. So this is X times Y. So it will do a pairwise multiplication. Then after that, we'll create a new variable called Z assigned to Z. But done immediately. So this data frame is still called XY, but now it has 3 columns there, X, Y, and Z. Z's value is the product of X and Y. Okay, let's move on to the same here. 2 times 1, 2 times 2, 2 times 3, 2 times 4, and so on, right? So that's the Z variable. We want to calculate the expected. Now it's quite straightforward. We want to calculate the expected value of Z column and the variance of Z column. That's quite straightforward, right? It's just a single list of numbers. Yeah, you don't even need to use some complex formulas. Yeah, just use these. Then next is yeah, basically I want to assign two products to make my life easier, X, Y, Z. I use Z to assign to a new variable called product. I just create a dummy product, just one product. The product is exactly the same as Z. So because I just want to reuse the rest of the code. So you use a view XY, you can see this data frame with 4 columns. So here is now I'm going to show a histogram. This is a histogram. So we have so many numbers, right? For 300 numbers, if you copy these 300 numbers into Excel, then you show it. These are the 300 numbers. And I'll just show the 300 numbers. I just show the 300. These are the 300 numbers, right? 1, 2, 3, 4, blah, 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 blah. There's so many numbers. There are 300 digits. Basically, we want to see a histogram of those digits. So this is a histogram. So this is neither a normal distribution, it is not a normal distribution, and it is not a uniform distribution. Then this is an overall exponential distribution. Right? So smaller values has more frequency, more observations, and when the value goes larger and larger, then there's less occurrence. Then the frequency fxy is actually simple. Fxy is simple. Fx times y is 1 over 300. It's just 1 over 300, right? 1 over 300. Because each of the outcome has equal probability. Now, instead of on this 300 piece of paper in the box, then each of the paper has a number of Z value there. So there are 300 Z value. Some occur more frequent. Some value, like say 2 appears 2 times, 3 2 times, 4 appears 3 times. 1 appeared only once because only 1 times 1 equal to 1. So different outcome has a different probability. But from this list of 300 values, each of them has the equal probability to be drawn from the box of 300 piece of paper. Okay, so that's one. REP function is called replicate function, and you create a value, then how many times that you want to repeat. Okay, that's the replicate function. Then calculate the population expectation of x times y, basically z. So your x prop is fxy. So we are creating a probability, new probability field. In fact, it is just 1/300, right? So for us, we just populate these 300 numbers. So R is, don't worry, I can save a lot of numbers. Yeah, then after that, you remember these two product, basically z times z's probability. So you have 300 numbers, so z times its corresponding probability. The probability is 1/300. Then we'll create a new value called PP product times probability, product times probability, product times probability. Then you have this PP, right? So once you have this PP, next is you sum them together, it's your expected value of Z, right? So that's the expected value of Z. It's also the expected value of X times Y. So just use X times Y. Now you get 89.25. Okay, so based on the formula of the property of expected value, right? Earlier we mentioned that is if X and Y are independent, then the expectation of X times Y is equivalent to the expectation of X times the expectation of Y. So we can verify what is the expectation of X. Earlier we have used EX. What is the one we calculate? 3.5. Yeah, that's a familiar number. E underscore Y, we run it. It's 25.5, right? So EX times EY happen to be 89.25. Okay, 89.25. So the reason it is independent is you are drawing a die. You roll a die. This die is independent from picking up 50 numbers, 50 pieces of paper from another box. So you pick up one number from the box does not influence the result of rolling a separated die, right? So they are independent. So, and we have verified that for independent events, the property of expectation holds here. Okay, so this is the first step. We have derived the expected value for X times Y. Excuse me. Next, you look at the variance. Calculate the population variance of Z. Variance Z. Variance Z is variance X times Y. So since we already have variance Z, that's quite straightforward and simple, right? Okay, so variance Z. So basically, we have this product field or the Z field. They are the same equivalent. So this time, let's say we use Z. So these are 300 numbers of Z. Z is X times Y. So we calculate the variance. The variance is this value minus the expected X and Y, which is 89.25, right? 89.25. Minus, we got another 300 numbers. Then after that, what do? We square it, right? We square it. You can type it parentheses first, then paste, right? Then powered 2. And this is power 2. Then next is you need to time the what? The probability of each outcome of these 300. So the probability is 1/300. You can do a 1/300. So these 300 numbers from the first part will time the 300 or 1/300, 300 times, right? Or you can use a replicate function. So they are the same. They will be the same. So that's the one, right? Then next is you need to sum them together, right? Sum them together. This should be the variance. So the variance is 5055.021. So that's the variance. So we can also calculate from here. So this is exactly the same formula. You run it, it's showing you that the variance is 5055.021, and your expected value of x times y equal to this number. So there's the alternative ways to use formula to calculate these because x and y are independent. So we start from here. Variance z. Oh, we want to calculate the variance z, right? Before we move the x times y into it. So you need to be aware there is a standard base formula, which is z, each individual of z value minus the expected value of z, right? Then we square it. Then we want to find the expected value of it. Expected value of this part is each individual times the probability of it, 1/300. Then sum them together. So this is an E part, okay? Then we expand the square. So z minus E square. Remove the expected y value first. It is z power 2 minus 2z, 2z times expected z, then plus expected square. Okay, so that's a standard algebra. Apply expectation, linearity of expectation. So this part, yeah, we'll rearrange a little bit, is equal to this one, we add expected there here, is equal to your expected z power 2, right? Z power 2 minus, so the linearity, minus expected of 2z times ez plus this part, right? Plus this part, okay? It says since ez is a constant, so this part is a constant. You need to take note, this part is a constant. Expected value of z is a constant, it doesn't change, right? As long as your z value has been fixed, which is a fixed list of x times y. So it's deterministic. So ez is a constant. This is a constant. So this is a constant, while z is a variable. Ez is a constant. So now the earlier above one become the 2ez becomes this part, right? Become this part. Easy is. Then you can move this 2ez out of this expected function, right? So 2ez is a constant, You get it out of the square bracket. Then the remaining one is ez. So times ez become 2ez. 2 times ez times ez. Okay, so that's the part. 2 times e, 2 times easy. Okay. Then this part becomes the easy squared. Okay, because easy is a constant. Easy is a constant value. Let's say 3. 3 power 2, which is 3 times 3 equals 9. That single number 9, what is the expected value of a single number 9? It is 9 itself, 9 itself. So it is equivalent to 3, which is expected value power 2. Okay, so that's one. So you move these two parts into the above, you will derive this formula. Variance z equals to z squared, get the expected value minus the expected value of z squared. Okay, so that's the formula. So from here, we're going to continue to move. Okay, so with this formula, then we continue to work on it. Okay, now. So now you let z equals to x times y, you move into it. Using this formula, you replace z by x times y. Z power 2 is x times y power 2. Ez is ex times y. By the way, this part is still a constant, okay? Since x times 2 power is x power times y power 2, right? So this is, then variance z equals to this part, right? Become this part. So z here, then this part doesn't change. If x and y are independent, right? So earlier we learned if x and y are independent, event you consider this one is called A times B. Okay, equivalent to EA times EB. Right? So we have this formula, right? So if x and y are independent, expected value of A times B is expected A times expected B. Then A is x squared and B is y squared. You put it inside, you will have this formula. Okay. Right. Okay, right. So these two right. This two is equation is correct, right? Then you continue to work from here, right? So now you notice this part becomes this. Okay, so your variance z becomes expected x power 2 times expected y power 2 minus this. No, this part is expected x times y is expected x times expected y. And then you time them together, then power it. So now you finally derive this formula, right? Derive this formula. So now what do we need? We need to compute these four expected value. These four expected value. Expected x we already have 3.5. Expected y we also have 25.5. Now we are going to calculate x squared and y squared and find their expected value. Okay. So how do we compute this one? So x powered xy. By the way, first we derive x. This is the x variable, right? This is the x variable. This is your x variable. Oh, this is the x variable. This is x variable, which 1 to 6, right? This is 1 to 6. You want to find your power. Then you have 1, 4, 9, blah, 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 right? Then you have your y variable. And the y variable power it. You have that list of 6 digits and 50 digits. Right there, time their corresponding frequencies. X times 2 times 1 over 6, just 1 over 6. Then you have this number, then you sum them together. So this is the 15.1167. So this is your expected x squared. 160. Then we have y squared, expected value of y squared is this value. Let's display it. Is 800 plus. So you have all 4 elements, right? So you have this one, which is about 15.17. This one is around 800 something, right? 850. So you get these 2 number time minus this. So you have this. So I have this. So just run it and have a look. This is the variance of x times y. Let's have a look at each individual component. X2, Y2, actually run this EX. Yeah, you can actually highlight it and just press run. Highlight them, just press run. It will just run the highlighted area. So you got these 4 numbers already. Now, then use this formula, the first 2 times to each other minus the second 2 times to each other, power it. So then you in the end you still get 5055.021. So this is the same value that we have derived earlier. So this time we're using a formula. So take some time to review and digest, okay, about how we actually derive the formula. So the thing here is, if you find that the formula is quite difficult to prove, then my way is, a suggestion is you just create this z column. As long as you have these z columns and it's a probability of 1/300, you can get it right without using any formula, any complex formula to get these four numbers. To get these four numbers, you don't really need. Okay, so let's move on from here. Okay, there are some tips about variance of x and y. If you're using a sample variance, you'll find it is different. Okay, so using a VAR function against the z value, you will get a different value. VAR xy $z. So we get 5071, which is not 5055. So because it's actually calculating sample variance. Instead of using fx is 1/300, it is using 1/300 minus 1. So the internal R function is calculating the sample variance. So at the meantime, for your awareness. Okay. Okay, so this is a pretty complicated one for you to digest. Question 3, straightforward. 50 students, number of students 50. Then I show the following. Then how many of you are 18 years old, 19, 20, 20. Okay, so that's one. So expected value. So create an age vector. So click everything. You have an age vector. So age of 5 numbers shown here. You have counts, how many individuals are there. So the probability is the counts divided by the sum of the counts. So these are the probability. The sum, yeah. So each individual count divided by the sum of all those. Then the sum of the probability of age must be equal to 1. So all the 1, 2, 3, 4, 5 numbers sum to 1. Then next is easy, right? Age, which is the x variable, a few of them times the probability. You get that one, then sum them together, you get this expected age of this class, 19.1 years old. Okay. So what's the probability of at least 20 years old? P greater than 20 years old. What is the probability? At least 20 years old. So at least 20 years old is these, right? The last three, excluding the first two, right? At least 20 years old. 5 to 1, basically the last three probability, right? So you have the probability, you have a look at the probability here is basically to teach you how to run some of the subset of the variable. So 1, 2, 3. You want the last three. So page is from 1, look, 1, 2, 3, 1, 2, 3. So 0 0.2, 0 0.2, 0 0.64, 0 0.5, 4, 5. So in total, you have 5 numbers, 3, 4, 5. You want to add 0 0.1, 0 0.04, and 0 0.02, right? So one way is just use this page. 3, 4. 3 column 4. So there are 3 numbers. The third one, fourth one, and fifth one. So then there are 3 numbers. Then sum them together. You highlight these parentheses. You get 0.616. So 0.16, 16%. Okay, at least 20 years old. So what you are obtaining here, the probability is a probability mass function. Probability mass function. You know, plot H, then the P underscore H, P underscore H. Yeah, seeing 18, the probability 19, 20, 21, then you don't have 23, 24, 25 for one occurrence. So that's the probability mass function, right? So for probability mass function, I want H equal or greater than 20, you can use 1 minus the one lesser than 20. Can also use to derive 41 minus the sum of probability pH and pH, the first two, right? The first two is 1. You also get 16%. 16%. Question 4, suppose that 3 random variable, blah, 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 from this one, and determine the value of, so this is to test you the linearity, right? So you move the coefficient out, that's fine, right? Then do with this. So it says analysis 2 times x1 minus 3 times x2 plus x3 minus 4 is equal to 2, get it out, expected value of x1 minus 3, so minus 3 here, no minus 3 going out, then plus 1 x3, the plus 1 ex3, then minus 4 is a constant, and move it out more. So ex1, 2, 3 equals to 5, so 2 times 5, blah, 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 right? So in the end, you get negative 4. Now, that's straightforward. So this is the linear additive property of the expectation. Question 5. Suppose that x and y are independent random variables for which variable variance x equal to 3, variance y equal to 2. Find the value of variance x plus y. Okay, x plus y. X plus y. Find the variance of, now you have more coefficient. Variance x 3, variance y equals to 2. Then variance x plus y equals to variance x plus variance y. So that's the variance property. Now you have coefficient coming. So you have 2 as a coefficient for x, 3 coefficient for y. To move the coefficient out, we need to get coefficient times power 2, right? Power 2. Power 2, then the second coefficient 3 power 2. Which is 9. Then a constant will be removed. Constant will not be used. Okay, so the new variance is 30. 30. So there's a sub question 3 that I added. So can you calculate variance 2x times 3y plus 1 equals to 1. So variance 6xy plus 1. You know plus 1, you can just ignore it because it's constant. Constant will be removed. So it is equivalent to variance 6xy. So you move the coefficient 6 out of this variance bracket. You need to power it. So power by 2 then. 36, 6 power 2, 36. So 36 variance x times y. In order for you to calculate variance x times y, x times y, remember earlier we have this variance formula, right? We have this variance formula using expected value. So where blah, 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 blah. Okay. So in the meantime, you will only know variance x equal to 3, variance y equal to 2. We actually do not know what is the expected value of x and y from this question. This question only tells us variance. This question doesn't reveal any of the expected value, right? You can have the same variance, but your expected value can change a lot. Say a die with 1 to 6 as face value, compare with another die has face value 11 to 16. These two die have the same variance. However, the face value or the expected value is different. One is 3.5, and that is 3.5 plus 10, that's 13.5, right? So in order to calculate the variance of x times y, we actually know we need to know what is the expected value of x and y, which we do not know at the meantime, right? So since we do not know, we will not be able to calculate the variance of x times y. Okay, so this is just an add-on for you. Now question 6. Suppose that a random can take a 5 value. This is again a very straightforward one. Equal probability. Then what is the variance of x? So equal probability. So x is this. So let's clean this. Clear this. X is this vector of 5. Then the fx is 0.2. So x times fx, this can also say x times 0.2. You'll get the same value because 0.2 will be reused. If there is a shorter vector, there's a longer vector. When there's a longer vector, the shorter vector will be reused or called recycled again. So expected value, okay, expected value. And the variance again straightforward. Then expected value and variance is this 4.56. So this is the expected variance of the population. Question 7. Question 7 is interesting. So you have 3 classes. I happen to teach 3 classes: Class A, Class B, Class C. Class A, it has an average score of 70 with standard deviation plus minus 2 marks. Class B mean is 80 marks and standard deviation 2. Yeah, class C is mean 70, standard deviation 1. So yeah. Okay, knowing the property, however, what will you do to convert A to B, cos A to cos B? So let's have a look of a few causes first. I'm doing simulations, so SA, SB, SC. So SA basically I have a lot of numbers draw from a R norm function, right? So R norm is normal distribution. So this is a normal distribution. R norm is draw how many number of samples from a normal distribution of mean and standard deviation. So this is draw 10,000 samples from mean and this from mean and standard deviation class A. So HIST SA. So this is a class A. Class A is distribution. Class B is centered at 80. Class C is narrow. In fact, it's narrow because the standard deviation is small. While histogram B, you see around plus minus 5 marks. Here is only plus minus about 2 marks. Here is also class A, plus minus 5 marks. Majority of the data, 5 marks. There. Define plotting the function for the histogram. So I just define another more fancy function. So in order to adjust from mean to 70 to 80, the variance remain unchanged. You just add 10 marks into the class A so that everyone in class A get a 10 marks bonus. So the average of the class A will be the same as the class B of 80 marks. So let's just visualize it. Okay, let's just visualize it. So this is the first question. Okay, original class A distribution centered 70 plus standard deviation of 2. Then you want to transform to the original B distribution, which is at 80. So you want to just shift it. So plus 10 marks, you will move from here to here at 10 marks. Now, variance will not change. When we are adding a constant into a variable, remember, right? So plus a C constant, your variance will not change. Adding a constant here. So alpha equals to 1, we don't do anything. Then we add a C into it. Now we just add 10 marks. Just add 10 marks, not times 10 marks, just add 10 marks. The variance will not change. Then your expectations property. you add C equals to 10 marks. C equal to 10 marks. Your X1 is your cos A's, each of individuals raw mark. Everyone plus the C 10 marks. Then you will have your expected value to be shifted from 70 to plus 10, which become 80. At the same time, your variance of the class will not change because you just add a constant, right? So this we're exploiting that two properties of expectation and variance to convert cos A average cos A to cos B distribution. So this is the first question. So this is the first question. Then second is saying cos A to C. Cos A and cos C has some differences. Cos A is mean 70 standard deviation 2. Cos C is mean 70 standard deviation 1. So in cos A class A, there's more variations in students' performance and score. Some scored high, some scored low, so the standard deviation is large. In class C, most of the students perform very stable, near 70, with very few marks variations. Most of it is very narrowly scoring around 70, right? So that's a problem. So let's move on. So now let's see. Move to C is divided by 2 plus 35. So this is 1 divided by 2 plus 35. Or you can do this plus 70 divided by 2. So these two results will be exactly the same. Okay, the same. Okay. So now let's visualize the second question. Let's visualize it. Okay, now original A distribution means 70 standard deviation 2. Original C distribution means 70 standard deviation 1. So what we're doing here is first we divide A by 2. Okay, we divide by A by 2. So alpha equals to 0. Alpha equals to 1 over 2, which is 0.5. So when we have alpha 0.5, your standard deviation is going to be reduced by half. Okay, here, right? Now alpha is 0.5. Okay, you move alpha out. So alpha becomes 0.5 power 2, right? So it becomes 0.25 times the variance. The variance is, how much is the variance? Variance of X. Your standard deviation is 2. Your variance is 4, right? So at standard deviation power 2 is your variance. So your original variance is 4, okay? 4 times 0.25, you get your variance 1, okay? Variance become 1. Then square root of 1, your variance or your standard deviation will be 1, okay? So that's how it is first being converted. But when you are dividing by 2, now your alpha here is 0.5, right? So your expected value of 70 marks will be reduced half as well, alpha equal to 0.5. So earlier your center, your mean value is 70. Now after you apply alpha equal to 0.5, your mean score of the class A, basically divide everyone by half. It's quite intuitive. Everyone's score will be halfen. So average 70 becomes 35. So this is what is effect here. Say A divided by 2. You will see the distribution now move to the mean value of 35 with standard deviation of 1. Now we want to change it back to 70. Right? So mean 70. So move from this chart to this chart. What do we do? Plus 35 marks, right? Plus 35 marks will move to here. And this transformed A distribution will be the same as the original C distribution. Mean value 70, standard deviation of 1. Okay, so this is what is being mentioned here. So you use divide by 2 plus 35, or you plus, sorry. C divided by 2 plus 35. Divide A to C. This form. Okay. Yeah, you can also do this. You can also do this. Plus 70 first divided by this. You should get the same result. Use the original one. This one, so the visualization will be better. Next is convert to standard norm. Okay, it's convert to standard norm. What is standard norm? Standard norm is zero mean univariance. So you have original A distribution, right? You divide by 2 minus 35. Okay, you divide by 2 first. Then you have move to 35, earlier 35. Standard deviation 1, then minus 35. So your mean value from 35 now will move to 0. So this is a Z transform A. Yeah, zero mean univariance. Now standard norm is zero mean univariance. Okay, so that's the one. That's question 3. Question 3. Okay, very good. Standard norm transformation. Okay, so this code and video will be available to you at the end of the week. So stay tuned and get review. Okay, I'll see you next week. Yeah.